Tonight, we're going to talk about the space between galaxies. Not the galaxies themselves, not the stars inside them, but the gaps, the vast, nearly absolute emptiness that separates one island of stars from the next. By the end of tonight, you're going to understand what those distances actually mean, how they compare to anything we have ever measured, and why the universe, which contains hundreds of billions of galaxies, is nevertheless almost entirely empty in ways that change how you see everything. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something familiar. The nearest large galaxy to our own is Andromeda. You've heard the name before. You may even know the rough distance, about 2.5 million light years. And if you're like most people, that number lands as something vast but abstract, a piece of information that sits in the mind without quite connecting to anything you can feel. Tonight, we're going to try to change that. Let's talk about what a light year actually is. Light moves at just under 186,000 miles per second. In 1 second, a beam of light could circle the Earth 7.5 times. In 1 minute, it travels from the Earth to the Moon and back with room to spare. In about 8 minutes and 20 seconds, it crosses the entire distance from the Earth to the Sun, 93 million miles, covered in the time it takes to make a cup of coffee. In 1 year, light travels roughly 5.88 trillion miles. That number is a light year, not a unit of time, a unit of distance. 5.88 trillion miles. Now hold that number and read the distance to Andromeda again. 2.5 million light years. 2.5 million times 5.88 trillion miles. The result, if you work it out, is roughly 14.7 quintillion miles. That is a 1 followed by 19 zeros. It is a number so far outside human experience that the only honest thing to say about it is that it does not fit inside any comparison we normally use. You cannot drive it. You cannot fly it. You cannot cross it with any technology that exists or that anyone seriously believes will exist in the coming centuries. But here is what makes it stranger. Andromeda is the nearest large galaxy to the Milky Way. It is essentially our next-door neighbor, and the distance to our next-door neighbor is 14.7 quintillion miles. Let's talk about how to put that in terms that feel more real. Voyager 1 is the most distant human-made object in existence. As of today, it sits roughly 15 billion miles from the Sun, which means it has been traveling for nearly 50 years and has crossed a distance that sounds enormous until you compare it to anything outside the solar system. The distance from Earth to Voyager 1 is approximately 0.01% of the distance to Andromeda. If the distance to Andromeda were a football field, Voyager 1 would have moved less than the width of a single strand of human hair from the goal line. In 50 years of flight at 38,000 miles per hour, our fastest spacecraft has barely begun. But the numbers by themselves are not the thing that changes you. What changes you is what the numbers imply. Let's talk about what Andromeda looks like from here. On a clear night, far from city lights, Andromeda is visible to the naked eye as a faint smudge near the constellation Perseus. It is one of the most distant objects a human being can see without a telescope. And when you look at it, you are looking at light that left Andromeda 2.5 million years ago. Modern humans had not yet existed when that light began its journey. The oldest confirmed stone tools are roughly 3.3 million years old. Homo sapiens as a species is perhaps 300,000 years old. The light you see when you look at Andromeda began its crossing of intergalactic space before our species walked the Earth. and it has only now reached your eyes. 2.5 million years of travel, and Andromeda, again, is the nearest large galaxy. Our next-door neighbor, the shortest gap between our island of stars and the next one. Here is where things get interesting, because the distance to Andromeda, staggering as it is not representative of intergalactic distances in general. It is, in fact, one of the smallest intergalactic distances that exists. The gap between the Milky Way and Andromeda is small because we are gravitationally bound to each other, part of the same small cluster of galaxies called the local group. Most of the universe's galaxies are separated by distances that make the Milky Way to Andromeda gap look like the distance between two houses on the same street. Let's talk about what happens when you look beyond the local group. The nearest galaxy cluster beyond our local group is the Virgo cluster, a dense collection of roughly 1,300 galaxies centered about 54 million light-years from Earth. The distance from us to the Virgo cluster is 21 times larger than the distance from us to Andromeda. And the Virgo cluster is not a distant object by extragalactic standards. It is our nearest large neighbor cluster, close enough that its gravity influences the motion of our own local group. Beyond the Virgo cluster lie hundreds of thousands of other galaxy clusters, stretching in every direction to the edge of the observable universe, 46 billion light-years away. But the numbers are almost the least interesting part of this. What they point toward, what they imply about the structure of everything we can see, is what tonight is really about. No one expects the universe's 200 billion galaxies to leave most of the cosmos essentially empty. No one predicts that the vast majority of the volume of the observable universe contains no galaxies at all, no stars, no planets, almost no atoms of any kind. And absolutely no one anticipates, when they first encounter the scale of intergalactic distances, that the universe is not a place full of things, but a place full of gaps, structured around almost incomprehensible amounts of nothing. That is what we are going to sit with tonight. Let's stay with Andromeda a little longer, because there is a dimension of the distance that we have not fully unpacked yet. When you look at Andromeda with the naked eye, or with any telescope, you are not seeing Andromeda as it is right now. You are seeing it as it was 2.5 million years ago. The light that left Andromeda while hominids were first shaping stone tools is only now reaching your eyes. What is happening inside Andromeda right now, in this exact moment? You cannot know. That information is in transit, crossing the intergalactic void at the speed of light, and it will not arrive for another 2.5 million years. No one expects this to feel as strange as it does. No one predicts, when they first think about the light travel time from Andromeda, how complete the separation really is. You are not looking at a distant galaxy in the way you look at a distant mountain. The mountain is there now, exactly as you see it, subject to the same physical present moment as you. Andromeda is not. The Andromeda that exists in the same present moment as you is invisible to you and will remain so for 2.5 million years. You are separated from your nearest galactic neighbor, not just by distance, but by time in a way that has no everyday equivalent. 2.5 million years ago, Andromeda looked somewhat different. The ratio of young blue stars to old red stars was slightly higher. Certain star-forming regions were more active. The positions of its satellite galaxies were different. The spiral arms were in slightly different orientations relative to our line of sight. None of these differences are enormous, because Andromeda is a stable, mature spiral galaxy, and its changes over 2.5 million years are modest. But the principle is what matters. The universe as we observe it is not the universe as it currently exists. It is the universe as it existed at the moment each piece of light left its source. distributed across a range of past moments proportional to distance. When we look at the Virgo cluster, 54 million light-years away, we see it as it was 54 million years ago. When we look at a quasar 10 billion light-years distant, we see the universe as it was 10 billion years ago. The telescope is a time machine that only goes backward, and the farther you look, the earlier the moment you are seeing. Let's talk about what happens when Andromeda arrives. The Milky Way and Andromeda are currently approaching each other at roughly 75 miles per second. The collision and merger will begin in approximately 4.5 billion years. For a long time, this was presented in popular science as an apocalyptic event. Two galaxies, each containing hundreds of billions of stars, slamming into each other. The reality is almost the opposite of apocalyptic, and understanding why tells you something essential about the emptiness that even galaxies consist of. Think about a galaxy as you might think about a room full of suspended cigarette smoke. The room has billions of smoke particles, but if you walk through the room, you do not collide with individual particles. The smoke passes through you. This is a rough analog for a galaxy collision. The stars inside each galaxy are separated by distances so enormous, in proportion to their own sizes, that two galaxies' worth of stars can pass through each other with essentially zero stellar collisions. The Sun is roughly 870,000 miles in diameter. The nearest star to the Sun, Proxima Centauri, is about 4.24 light-years away, which works out to roughly 25 trillion miles. The ratio of the star's diameter to the gap between stars is roughly 1 to 30 million. If you shrank the Sun to the size of a golf ball, Proxima Centauri would be another golf ball about 12 miles away. A vast, mostly empty volume between them. When two galaxies collide, the stars mostly pass by one another at those kinds of separations. The odds of any single star colliding with another during a full galaxy merger are astronomically small. No star in the Milky Way is expected to directly collide with any star in Andromeda. What does happen is that the gravity of each galaxy's mass distorts the motion of the stars in both systems. As the two galaxies pass through each other and swing around and merge over a period of hundreds of millions of years, stars are flung into new orbits. Some are ejected entirely from both systems. The spiral arms of both galaxies are disrupted. Long tidal streams of stars are drawn out into the surrounding space. The gas clouds that are the raw material for star formation are compressed by the interaction, triggering bursts of new star formation. Eventually, after several passes and billions of years, the two spirals settle into a single large elliptical galaxy. Our Sun will almost certainly still exist at this point. It has enough hydrogen to burn for another 5 billion years. Whether any Earth-like planet orbiting it will still be habitable is a different question, having more to do with the Sun's gradual brightening than with the galaxy collision itself. The merged galaxy, which astronomers have playfully named Milkomeda, will not look like either parent. It will not have spiral arms. It will be a flattened elliptical cloud of billions of old stars, slowly aging, its star formation mostly quenched because the collision will have used up most of the available gas. At its center will be a massive black hole formed from the merger of the supermassive black holes at the center of both current galaxies. Absolutely no one anticipates, when they hear that two galaxies are going to collide, that the event will play out over billions of years and result in something that looks like a quiet oval of old stars rather than a firestorm. But the scales of space and time make it so. The collision is real, the merger is real, but it is the merger of two vast emptinesses, each decorated with occasional stars, and the outcome is a larger emptiness decorated with more stars arranged differently. And after all of that, after the 4.5 billion year approach, the collision, the merger, the billion years of settling, Andromeda will look out at a universe in which almost everything has already crossed beyond the cosmic event horizon. The galaxies we can see today will be gone. The cosmic web will be undetectable. The only thing remaining will be the faint, cold remnant of the merged galaxy itself, cooling slowly in an expanding void that stretches in every direction without limit. The merger of Andromeda and the Milky Way is, on the longest timescales, a footnote. The real story is the expansion of the universe and the way it is slowly, inexorably, separating everything that is not gravitationally bound. The distances between galaxies are not just large, they are growing, and nothing we know of can stop that. And here is what makes those gaps even harder to process. The Milky Way and Andromeda are not isolated. They belong to a collection of galaxies called the Local Group, a loose gravitational family of roughly 54 known members spread across a region about 10 million light-years in diameter. 10 million light-years. 4 times the distance to Andromeda, in every direction. That sounds like a lot of galaxies in a manageable space. But let's talk about what the Local Group actually looks like when you take the numbers seriously. Of those 54 members, only 2 are large spiral galaxies, the Milky Way and Andromeda. Everything else is a dwarf galaxy, most of them so faint that astronomers are still discovering new ones as telescope sensitivity improves. The large and small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way, are among the larger dwarf satellites, but they are still tiny compared to the 2 main spirals. The Triangulum Galaxy, sometimes called M33, is the 3rd largest member of the Local Group and is roughly 1/10 the diameter of the Milky Way. So the Local Group is mostly 2 large galaxies and dozens of small companions, arranged in a roughly elongated cloud, held together by mutual gravity. It is the only region of the universe where galaxies are actually getting closer to one another rather than farther apart. Andromeda and the Milky Way are approaching each other at roughly 75 miles per second. In about 4.5 billion years, they will collide and merge into a single large elliptical galaxy. But the Local Group, 10 million light-years across, is itself a tiny feature in the larger map. Let's talk about the Virgo cluster and what lies beyond it. The Virgo cluster is the nearest major galaxy cluster to the Local Group. It sits about 54 million light-years from Earth. It contains roughly 1,300 confirmed galaxies, ranging from dwarf ellipticals barely the size of large globular clusters to massive elliptical giants like M87, the galaxy at whose center astronomers photographed the first image of a black hole shadow in 2019. M87 alone contains an estimated 1 trillion stars. The distance from Earth to the Virgo cluster is 21 times larger than the distance from Earth to Andromeda. But what matters more than that ratio is what it implies. If you drew a map of the Local Group to scale, with the Milky Way at the center, the farthest members of the Local Group would sit about an inch from the edge. The Virgo cluster, on the same map, would be 21 inches away. Not a neighboring room, a different building. And the Virgo cluster is the center of a much larger structure. Together, the Local Group and the Virgo cluster and hundreds of other galaxy groups are all part of the Virgo Supercluster, also called the Local Supercluster. The Virgo Supercluster spans roughly 110 million light-years and contains around 100 galaxy groups. For a long time, it was considered one of the largest known structures in the universe. But here is where things get worse. In 2014, astronomers Brent Tully and Courtois and their team remapped the local universe by tracking how all the galaxies near us are moving under gravity. What they found was that the Virgo Supercluster is not a standalone structure. It is merely one lobe of a much larger system they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is our actual home supercluster. It spans roughly 520 million light-years and contains the mass equivalent of 100 quadrillion suns, organized into a web of filaments flowing toward a central gravitational attractor called the Great Attractor. No one expects the local group to seem as small as it does from this vantage point. No one predicts, when they first look at a map of the Milky Way and Andromeda approaching each other across 2.5 million light-years, that the entire region they occupy together would be a barely visible dot on the map of Laniakea. Absolutely no one anticipates the degree to which what feels like a vast cosmic neighborhood turns out to be a single suburb at the edge of a structure containing hundreds of thousands of galaxies. Let's talk about what sits beyond even Laniakea. Laniakea is one supercluster among many. The Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster to the south of us. These are our equivalent scale neighbors, each containing comparable numbers of galaxy groups, each separated from Laniakea by hundreds of millions of light-years of intergalactic space. The Shapley supercluster, the densest known collection of galaxies in the nearby universe, sits about 650 million light-years away and contains so much mass that its gravity pulls the entire local group toward it at measurable speed. If the distance from Earth to Andromeda were 1 step, the distance from Earth to the Shapley supercluster would be 260 steps, and the Shapley supercluster is still in the local, nearby universe. In terms of the observable universe, which extends 46 billion light-years in every direction, even the Shapley supercluster is essentially next door. But here is what tonight is really pointing toward. All of these clusters, all of these superclusters, all of these structures, they are arranged not randomly, but in a specific pattern. The matter in the universe is organized into a cosmic architecture, a web of filaments and walls and nodes surrounding vast regions of almost perfect emptiness. By the end of tonight, we are going to sit inside those empty regions and understand what they mean. And what they mean is stranger than almost anyone expects. There is something the cosmic web is built on that we have not talked about yet. Something that outweighs all the visible galaxies and stars and gas by a factor of roughly 5 to 1. Dark matter. And the structure of the intergalactic distances, the reason the filaments and voids exist where they do, is inseparable from the distribution of this invisible component of the universe. Let's talk about what dark matter has to do with the space between galaxies. Dark matter is not fully understood. We cannot detect it directly. It does not emit, absorb, or reflect light. Every measurement we have of it is indirect, coming from the gravitational effects it exerts on visible matter. But those effects are unmistakable. The rotation curves of galaxies, the way they spin faster than the visible matter alone could account for, require the presence of enormous halos of invisible matter surrounding each galaxy. The gravitational lensing of light around galaxy clusters shows matter present where no visible matter exists. The cosmic microwave background fluctuations fit the observed large-scale structure of the universe only if dark matter is included in the models, with approximately 5 times the density of normal matter. And dark matter has its own web. It preceded the visible cosmic web. The filaments and voids and clusters of galaxies we see today are, in a real sense, the visible traces of a pre-existing dark matter scaffold. In the early universe, the slight overdensities in the distribution of dark matter grew under gravity. Dark matter flowed along the paths of least resistance, accumulating at the intersections of what would become filaments, leaving the interior of what would become voids progressively emptier. Normal matter, gas, and eventually stars followed the dark matter into those scaffolded structures. The cosmic web of visible galaxies is a painting on top of an invisible skeleton. The halos of dark matter surrounding individual galaxies extend far beyond the visible stars and gas disk. The Milky Way's dark matter halo, by most estimates, extends somewhere between 200,000 and 400,000 light-years from the galactic center. The visible disk of stars extends only about 100,000 light-years. The dark matter halo is not a thin shell around the galaxy. It is a massive, roughly spherical cloud that the galaxy sits inside. When two galaxies approach each other, their dark matter halos begin interacting long before their visible disks do. No one expects dark matter to be so structurally important until the simulations make it unavoidable. No one predicts, in the early days of large-scale structure modeling, that a universe with only normal matter cannot produce the web of filaments and voids we observe. Absolutely no one anticipates how completely the visible universe turns out to be a secondary structure, organized by the gravitational influence of something that emits no light at all. Let's talk about the simulations that let us see the dark matter web. One of the most successful tools in modern cosmology is the N-body simulation. Starting from the density fluctuations measured in the cosmic microwave background, astronomers use supercomputers to model how billions of mass particles evolve under gravity over 13.8 billion years. The results can then be compared to the observed large-scale structure of galaxies. The agreement is extraordinary. The Millennium simulation, run at the Max Planck Institute for Astrophysics in 2005, tracked 10 billion particles through the history of the universe. It produced a cosmic web strikingly similar to the one observed in galaxy surveys like the Sloan Digital Sky Survey. The filaments, the voids, the clusters at intersections all emerged from the simulation without being programmed in directly. They emerged from the physics of gravity applied to the initial conditions, exactly as the universe did. The illustrious TNG simulation, a more recent effort that includes not just dark matter but also gas dynamics, star formation, and black hole feedback, has pushed the precision further. It produces synthetic universes that reproduce not just the large-scale structure, but also the properties of individual galaxies with remarkable fidelity. The simulations confirm that the distances between galaxies are not random. They are the product of a specific physical process playing out over cosmic time. The voids in those simulations are particularly striking. In the simulations, as in the real universe, the voids are not static. They grow. Dark matter continues to flow out of underdense regions and into filaments and clusters. The void interiors become progressively emptier as the simulation runs. And in the simulations with dark energy, the expansion of space accelerates, and the rate at which the voids deepen accelerates with it. Let's talk about the satellite galaxy problem, because it is one of the few places where the simulations and the observations do not fully agree. Standard dark matter models predict that a galaxy the size of the Milky Way should have hundreds of satellite dwarf galaxies orbiting it, each corresponding to a smaller dark matter subhalo captured by the main halo's gravity. We observe roughly 50 to 60 satellites of the Milky Way, depending on the survey sensitivity. This discrepancy, known as the missing satellites problem, has been debated since the late 1990s. Several explanations have been proposed. The most widely accepted is that reionization, the period when the first stars and quasars ionized the universe's hydrogen, about 1 billion years after the Big Bang, was so energetic that it heated and expelled the gas from small dark matter subhalos, preventing them from forming visible galaxies at all. The dark matter subhalos exist in this picture. They simply never lit up. We would be living surrounded by hundreds of invisible dark satellites, dwarfs we cannot see because they never formed enough stars to detect. As survey sensitivity improves, the census of Milky Way satellites keeps growing. The Large Synoptic Survey Telescope, now operational as the Vera Rubin Observatory, is expected to find dozens more faint satellite galaxies. The missing satellites problem may be more a problem of observation depth than a fundamental failure of the dark matter model. But the satellite galaxy problem is a reminder that the distances between galaxies and the counts of galaxies are numbers that change as our instruments improve. The 2 trillion galaxies estimated to exist in the observable universe is itself a number that has changed dramatically over time. In 2016, astronomers Christopher Consolis and colleagues used Hubble Space Telescope data and a model of how galaxies evolve to estimate that the total count of galaxies in the observable universe is around 2 trillion, roughly 10 times higher than previous estimates. The earlier number of 200 billion was itself revised from even earlier, smaller estimates. Each improvement in sensitivity reveals more structure in the distances between things. The intergalactic gaps are not just empty. They are full of things we cannot yet see. But the distances we have been talking about tonight are not simply stated as facts. They were measured. And the history of how humans learned to measure the distances between galaxies is one of the most compelling detective stories in the history of science. Understanding how we know what we know about the intergalactic gaps changes what those gaps mean. Let's talk about the cosmic distance ladder. Measuring distances in space is not a single method. It is a series of methods, each calibrated against the previous one, each reaching a little farther than the last. The process is called the cosmic distance ladder because you build it rung by rung, with each rung dependent on the accuracy of the one below it. And for most of human history, we could not even see the first rung clearly. The nearest stars are measured by parallax. This is the same technique that makes your finger appear to shift position when you alternately close your left eye and your right. As the Earth orbits the Sun across a diameter of about 186 million miles, nearby stars appear to shift slightly against the background of more distant stars. By measuring that angular shift twice, 6 months apart, astronomers can calculate the distance to a nearby star with high precision. The technique works reliably out to a few thousand light years. Beyond that, the angular shifts become too small to measure accurately from Earth. For distances beyond parallax range, astronomers rely on what are called standard candles, objects whose intrinsic brightness is known, so that their distance can be inferred from how dim they appear. The most important of these, the one that cracked open the intergalactic distances, is the Cepheid variable star. In 1908, Henrietta Swan Leavitt was working as a human computer at the Harvard College Observatory, cataloging stars in photographic plates from the small Magellanic Cloud. She had no professorship, no formal recognition by the institution, and limited authority to direct her own research. What she had was access to thousands of photographic plates and an extraordinary attention to pattern. What she found, in a systematic study she published in 1908 and expanded in 1912, was that a particular type of pulsating star, the Cepheid variable, had a precise relationship between its period of pulsation and its intrinsic luminosity. Cepheids that pulse slowly were intrinsically brighter. Cepheids that pulse quickly were intrinsically dimmer. And the relationship was consistent enough to use as a measuring tool. Because all the Cepheids in the small Magellanic Cloud were at essentially the same distance from Earth, their apparent brightnesses varied only because of their intrinsic luminosities, not their distances. Leavitt could therefore chart the period luminosity relationship without knowing the actual distance. Once you knew the intrinsic luminosity of any Cepheid from its period, you could calculate its distance from how bright it appeared in the sky. The implications took more than a decade to be fully recognized. In the early 1920s, there was a famous dispute in American astronomy known as the Great Debate. Harlow Shapley argued that the spiral nebulae seen in telescopes were clouds of gas within the Milky Way, that the Milky Way was the entire universe. Heber Curtis argued that the spiral nebulae were independent star systems, island universes comparable in scale to the Milky Way, at enormous distances beyond it. No one expected the resolution to come as quickly as it did. In 1923, Edwin Hubble identified a Cepheid variable star in what was then called the Andromeda Nebula. He measured its period, applied Leavitt's period luminosity relationship, and calculated a distance. The result was roughly 900,000 light-years, later revised to about 2.5 million light-years as calibrations improved. It was far beyond the edge of the Milky Way by any measurement. The Andromeda Nebula was not a nebula at all. It was a separate galaxy. The universe had just gotten enormously larger in a single observation. But Cepheid variables have a limit. They are individual stars, and even the largest can only be detected by our best telescopes out to about 100 million light-years. Beyond that, they are too faint to resolve. To measure larger intergalactic distances, astronomers needed a brighter standard candle. Let's talk about Type Ia supernovae and what they revealed. A Type Ia supernova occurs when a white dwarf star in a binary system accumulates enough mass from its companion to reach a critical threshold, roughly 1.4 times the mass of the Sun, and explodes. Because all Type Ia supernovae are triggered by the same physical threshold, they produce roughly the same intrinsic luminosity at peak brightness. They are bright enough to be seen across billions of light-years, and they can be detected and measured from Earth with modern telescopes. In 1998 and 1999, two independent teams of astronomers, the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project led by Saul Perlmutter, announced results that won the 2011 Nobel Prize in Physics. Using Type Ia supernovae as distance markers, they had measured the expansion rate of the universe at various epochs. The expectation had been that the expansion should be slowing down over time, as gravity braked the initial expansion from the Big Bang. What both teams found independently was the opposite. The expansion was speeding up. Something was driving it faster and faster. That something became known as dark energy, and it remains the dominant constituent of the universe's energy budget, accounting for roughly 68% of the total. But the story does not end there. As measurement techniques have improved, a problem has emerged. The rate of expansion measured using standard candles like Type Ia supernovae does not match the rate predicted by measurements of the cosmic microwave background, the faint glow of the early universe left over from about 380,000 years after the Big Bang. The supernova measurements yield an expansion rate of about 45 miles per second per megaparsec. The CMB predictions yield about 42 miles per second per megaparsec. The discrepancy is small but stubbornly persistent and statistically significant. It is called the Hubble tension. and it may be one of the most important unresolved problems in modern cosmology. The Hubble tension matters to the subject of intergalactic distances because it means we are not entirely certain how fast the distances between galaxy clusters are growing. Our two best methods for measuring that growth disagree. One possibility is that there is systematic error in one or both methods, something subtle that has not been accounted for. Another possibility is that the discrepancy is real, pointing toward new physics, some feature of dark energy or dark matter, or the early universe that current models do not contain. The James Webb Space Telescope, launched in December 2021 and fully operational by 2022, has now measured Cepheid variables and type Ia supernovae with greater precision than was previously possible. The early JWST results have so far not resolved the tension. They have, if anything, confirmed that both measurements are accurately made and the discrepancy is real, which means the distances between galaxies may be growing at a rate that our current best theory of cosmology does not fully explain. We are still climbing the distance ladder, and some of the rungs do not quite meet. The pattern of the universe at large scale is unlike anything you encounter in daily life, and unlike anything the early 20th century astronomers expected to find when they began mapping the cosmos. Let's talk about the cosmic web. In the 1980s and 1990s, as sky surveys began mapping the positions of hundreds of thousands of galaxies, a picture emerged that stunned the researchers doing the mapping. Galaxies were not scattered evenly through space. They were not distributed randomly, the way grains of sand might scatter if you tossed a handful into a box. Instead, they were arranged in thin curved sheets and long, thin strands, surrounding enormous empty regions where almost nothing existed. The structure looked, on the larger scales, like a foam of soap bubbles, or the internal structure of a sponge. The walls of the foam were where galaxies clustered. The interior of the bubbles was where almost no galaxies existed at all. This structure is called the cosmic web. It is the large-scale organization of all the matter in the observable universe. There are three main components: filaments, which are long, thread-like structures connecting galaxy clusters at their intersections; walls, which are flattened sheets of galaxies between the voids; and voids, which are the enormous empty regions surrounded by the filaments and walls. The filaments are among the largest coherent structures in the universe. The Sloan Great Wall, identified in 2003 by researchers analyzing the Sloan Digital Sky Survey, is a filament roughly 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, identified in 2013 and updated in subsequent years, may be as large as 10 billion light-years across, making it one of the largest known structures in the observable universe. But the most important thing to understand about the filaments is not their size. It is what sits between them. No one expects the voids to be as large as they are. No one predicts, when they first encounter the structure of the cosmic web, that most of the observable universe by volume is not filament or wall, but void, not galaxy, not star, not even diffuse gas, just space, nearly empty, extended across hundreds of millions of light-years in every direction. Let's talk about what a void actually is. The Bootes void was identified in 1981 by astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman. They were conducting a survey of galaxies in the direction of the constellation Bootes, expecting to find a more or less uniform distribution. What they found instead was a region of space roughly 250 to 330 million light-years in diameter, containing almost no galaxies at all. In a sphere that large, astronomers expected to find thousands of galaxies, they found initially 60. Subsequent deeper surveys have refined that number somewhat, but the Bootes void remains one of the largest and most empty known regions of the universe. Imagine for a moment a comparison that tries to bring this to human scale. The diameter of the Bootes void is roughly 130 times the distance from us to Andromeda. If the Milky Way were located at the center of the Bootes void, our nearest large neighbor galaxy would not be Andromeda at 2.5 million light-years. It would be something on the far wall of the void, at a distance of perhaps 150 to 160 million light-years. We would look out from the Milky Way into a sky that appeared, for all practical purposes, completely empty. The nearest galaxy bright enough to see with the naked eye would be something like 60 times farther away than Andromeda is from us now. The night sky might still contain stars within our own galaxy, but everything beyond the Milky Way's edge would be dark. A civilization in the Bootes void would not know, for a very long time, whether anything else existed. But the Bootes void is not the largest known void. The KBC void, named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who mapped it in 2013, is a region roughly 2 billion light-years in diameter of lower than average galaxy density. What is unusual about the KBC void is where we appear to be relative to it. We appear to be inside it. The Milky Way and the local group and the Virgo cluster and Laniakea are all near the center of a vast underdense region of the universe, a region where galaxy density is roughly 20% below the cosmic average. We are not at the densest point in the cosmic web. We are in a quiet suburb near the center of one of its larger voids. Absolutely no one anticipates, before the surveys that revealed it, that the universe would turn out to be organized this way, that the dominant feature of the cosmos at the larger scales would not be the matter, but the absence of it. The voids are not gaps between things. They are the primary texture of the universe. The filaments and walls, where all the galaxies and stars and planets and life live, are the thin, narrow edges of structures that are mostly absent. Let's talk about what the voids tell us about the history of everything. The voids exist because of the way gravity works over cosmic time. In the very early universe, matter was distributed almost uniformly, with only tiny quantum fluctuations creating slight overdensities and underdensities. Gravity pulled on those slight overdensities, attracting more matter, making the dense regions denser. The underdense regions, pulling slightly less, lost matter to their denser neighbors. Over hundreds of millions of years, the rich got richer and the poor got emptier, as matter drained from the underdense regions along filaments into the dense knots where galaxy clusters would eventually form. The result was the cosmic web. The voids are the original underdense regions, now amplified by billions of years of matter flowing out of them. They are not holes punched in the fabric of space. They are the original low points, emptied by the same force that built the galaxies and clusters in the filaments. And as the universe expands, those voids grow larger. The matter at the edges of the voids continues to be pulled toward the filaments and clusters, leaving the interior of the voids cleaner and emptier over time. The voids are not static. They are deepening. In the far future of the universe, the voids will dominate the landscape even more completely than they do today. By the end of tonight, we are going to look at what fills those voids and at what the expansion of space is doing to the distances between galaxies, and at what all of this means for any hypothetical civilization that might one day want to cross the intergalactic gulf. The answers to all three of those questions are stranger than almost anyone predicts. The voids of the cosmic web are not simply empty regions. They are environments. And the galaxies that exist inside them are different from the galaxies in the filaments and clusters in ways that tell us something important about how isolation shapes evolution, cosmic or otherwise. Let's talk about void galaxies. Most galaxies exist in dense environments. They are members of clusters or groups, surrounded by dozens or hundreds of neighbors within a few million light years. This environment shapes them. Galaxies in clusters experience ram pressure stripping, where the dense intra-cluster medium strips gas from a galaxy as it moves through the cluster, starving it of the fuel for new star formation. They experience tidal interactions with neighboring galaxies, which can trigger bursts of star formation or distort spiral arms into irregular shapes. They can be cannibalized by larger galaxies, feeding the growth of massive ellipticals at cluster centers. Galaxies in voids experience none of this. They live in near isolation, separated from their nearest neighbors by distances many times larger than their own diameters. The effects of this isolation are measurable. Void galaxies tend to be bluer and younger in their stellar populations. Blue galaxies are actively forming stars, converting hydrogen into stellar fusion. The redness of many cluster galaxies reflects an older stellar population, their gas consumed or stripped away, their star formation long since quenched. Void galaxies, still rich in gas and free from the environmental pressures of crowded environments, continue to form stars at rates that cluster galaxies of the same mass often no longer can. Void galaxies also tend to be less massive and less structurally developed. In the dense environments of filaments and clusters, galaxies grow through mergers and cannibalism. In voids, mergers are rare because the distances between galaxies are so large that gravitational encounters happen infrequently. A void galaxy is like a community that has never had trade partners. It grows slowly, on its own resources, without the stimulus of interaction. The existence of void galaxies tells us that galaxy formation can proceed even in the most underdense environments the universe offers. But the rate is slower, the outcomes different, the timeline stretched. A spiral galaxy in the Bootes void has been living for billions of years, essentially alone. Let's talk about the largest known voids and supervoids. The term supervoid is used for voids that are significantly larger than typical cosmic voids, which themselves range from about 30 to 300 million light years. Supervoids are rare concentrations of emptiness, regions where the underdensity extends over scales that challenge the structure-forming models of the universe. The most discussed supervoid in recent cosmology is the Eridanus supervoid, sometimes called the CMB cold spot supervoid. The cosmic microwave background, the ancient radiation from 380,000 years after the Big Bang, has one unusual feature in the direction of the constellation Eridanus, a region about 5 degrees across in the CMB map that is slightly colder than the surrounding background, the CMB cold spot. Cold spots in the CMB are regions where the early universe was slightly less dense. As photons from the early universe travel through a void, they lose a small amount of energy to the gravitational gradient of the void, an effect called the integrated Sachs-Wolfe effect. A supervoid in the right position along the line of sight could, in principle, imprint a cold spot on the CMB. In 2015, astronomers Istvan Sapudi and collaborators announced the discovery of a supervoid roughly 1.8 billion light-years across in the direction of the CMB cold spot, at a distance of about 3 billion light-years. It was, at the time, the largest known void. Its existence provided a possible natural explanation for the cold spot. But subsequent analysis has raised questions about whether the supervoid alone is large enough and deep enough to account for the full observed cold spot, leaving open the possibility that some combination of supervoid and statistical fluctuation, or potentially something more exotic, is responsible. Absolutely no one anticipates, when looking at the smooth map of the CMB, that the tiny temperature differences scattered across it contain embedded stories about the large-scale structure of the universe billions of years after the CMB was emitted. The CMB is not just a relic of the early universe. It is also a screen onto which the large-scale structure of the intervening universe, the voids and filaments and clusters, has imprinted its signature as the ancient light passed through. Now let's talk about the void we might be inside. The KBC void, or Keenan-Barger-Cowie void, named for the 2013 paper by Ryan Keenan, Amy Barger, and Lennox Cowie, is a region of lower than average galaxy density, roughly 2 billion light-years in diameter, centered near the Milky Way. The local galaxy density within the KBC void appears to be about 20% below the cosmic average. We appear to live in the relatively underdense interior of this structure, near its center. The KBC void has attracted significant attention in recent years because it may offer a partial solution to the Hubble tension. One contribution to the apparent discrepancy between local and CMB-derived expansion rates could be that we are inside an underdense region. In an underdense void, the local expansion rate would be slightly elevated above the cosmic average because matter flows out of voids toward the surrounding denser filaments and clusters. If the local expansion rate is elevated because we are inside the KBC void, then measurements of expansion using nearby standard candles would overestimate the global Hubble constant, which would bring the local measurement partially toward agreement with the CMB-derived value. How large this effect is remains contested. Some analyses suggest it could account for a significant fraction of the tension. Others argue it cannot account for more than a small fraction. The debate is ongoing, and the data needed to resolve it are still being gathered by surveys like the Dark Energy Spectroscopic Instrument and the upcoming Vera Rubin Observatory. But the possibility that our measurement of the universe's expansion rate is partially distorted by the void we happen to live inside is a remarkable reminder of the position we occupy in the cosmic web. We are not at the dense center of a rich galaxy cluster. We are in an underdense region at the edge of a supercluster that is itself located within a billion light-year void. Our picture of the universe is colored by where we sit within it. And where we sit, it turns out, is in the quiet interior of one of the universe's larger empty spaces. No one predicts this kind of geographical self-awareness when they first begin to map the cosmos. No one expects that the act of measuring the universe's expansion rate will eventually require us to account for the local environment of the Milky Way specifically, as though the voids and filaments around us are not just background scenery, but an active distortion of our measurements. Absolutely no one anticipates, in the early days of extragalactic astronomy, that the question of where we are in the cosmic web would turn out to matter for the most fundamental constants we use to describe the universe. The voids are not just large empty regions. They are the context in which we do our science. And we are, apparently, inside one. There is a period in the history of the universe that astronomers call the cosmic dark ages. Not a metaphor. A literal description of a time when the universe contained no sources of light at all. And understanding the cosmic dark ages changes what we understand about the intergalactic medium and why the space between galaxies is structured the way it is today. Let's talk about the first few 100 million years. After the Big Bang, the universe was hot and dense and opaque. as it expanded and cooled, within the first 380,000 years, it reached a temperature where electrons could combine with protons to form neutral hydrogen. The universe became transparent for the first time. Photons decoupled from matter and streamed freely through space. Those photons are what we observe today as the cosmic microwave background, the faint afterglow of this moment of transparency, filling the sky uniformly from every direction. After that transition, the universe entered the cosmic dark ages. The hydrogen and helium formed during the first 3 minutes, before the universe was cool enough to form neutral atoms, had settled into a uniform cold neutral gas. No stars existed yet, no galaxies, no quasars, no sources of visible light of any kind. The universe was dark, and the intergalactic medium that would eventually carry the signatures we observe today was a neutral hydrogen gas, extending uniformly in every direction. Then gravity got to work. The slight overdensities in the hydrogen distribution, seeded by quantum fluctuations in the first moments after the Big Bang and imprinted on the CMB, grew under their own gravity over tens to hundreds of millions of years. The overdense regions pulled in surrounding gas, building up the first dark matter halos, and within those halos, gas compressed and cooled and fragmented into the first stars. This is called cosmic dawn. The first stars were very different from the stars we see today. They formed from gas that was almost entirely hydrogen and helium, with no heavy elements at all. Without heavy elements to radiate heat efficiently, the gas clouds that formed the first stars could not cool as effectively. The result was that the first stars, called population 3 stars, were almost certainly enormously massive, potentially hundreds or even thousands of times the mass of the Sun. At those masses, they burned ferociously hot and died quickly. They lived for only a few million years, but while they lived, they flooded the universe around them with ultraviolet radiation. No one expects the first stars to be so extreme. No one predicts, in the early models of stellar formation, that the absence of heavy elements would produce stellar masses so far beyond anything that forms today. Absolutely no one anticipates, before the detailed chemistry of primordial gas formation is worked out, how different the first epoch of stars would be from everything that followed. And those ultraviolet photons from the first stars did something crucial. They began to ionize the neutral hydrogen of the intergalactic medium. Hydrogen, when struck by a sufficiently energetic photon, releases its electron and becomes a proton, a positively charged hydrogen ion. As the first stars and eventually the first quasars poured ultraviolet radiation into the surrounding medium, bubbles of ionized gas began to form around each source. Over time, the bubbles expanded and overlapped. In a process called reionization that lasted from roughly 150 million to about 1 billion years after the Big Bang, the entire intergalactic medium transitioned from neutral hydrogen to the ionized plasma it consists of today. Reionization is one of the most dramatic phase transitions in the history of the universe. Before it, a dark, neutral universe with light appearing only in small bubbles around the earliest stars. During it, an increasingly patchy universe of overlapping ionized bubbles and shrinking neutral regions. After it, the transparent, ionized intergalactic medium that has existed for the last 12 billion years, through which we observe the cosmic web today. Let's talk about how we know reionization happened. The primary evidence comes from the spectra of distant quasars. A quasar is an extremely luminous galactic nucleus powered by matter accreting onto a supermassive black hole. Quasars are bright enough to be seen across the observable universe, and their spectra, the rainbow of light they emit at different wavelengths, carry the imprint of everything the light passed through on its way to us. Neutral hydrogen is an extremely efficient absorber of photons at a specific ultraviolet wavelength corresponding to the Lyman alpha transition. When light from a quasar passes through a region of neutral hydrogen, hydrogen atoms absorb photons at this wavelength. If the universe contained significant amounts of neutral hydrogen along the line of sight to a distant quasar, the quasar spectrum would show a deep absorption trough on the blue side of the Lyman alpha emission line. In 1965, James Gunn and Bruce Peterson predicted that if neutral hydrogen existed in the intergalactic medium along the line of sight to distant quasars, it would produce exactly this absorption trough. For decades, the spectra of quasars at all observed redshifts showed no such trough, implying that the intergalactic medium at those epochs was already ionized. But as surveys pushed to higher and higher redshifts, finding quasars at greater and greater distances corresponding to earlier and earlier cosmic epochs, the trough began to appear. Quasars at redshifts above about 6, corresponding to times when the universe was less than 1 billion years old, showed the Gunn-Peterson trough in full, indicating that at those epochs the intergalactic medium was substantially neutral. This is the observational fingerprint of reionization. We can see, in the spectra of distant quasars, the transition from a neutral to an ionized intergalactic medium playing out across cosmic time. Before we get started on what this means for the intergalactic distances we have been discussing tonight, consider what it says about the relationship between galaxies and the space between them. Reionization is not something that happened to the intergalactic medium independently of galaxies. It was caused by the galaxies and the first stars. The light from the earliest sources of radiation changed the physical state of the entire intergalactic medium, transforming it from something opaque to ultraviolet light into something transparent. The galaxies shaped their environment. The environment then shaped subsequent galaxy formation, because the ionizing radiation that made the medium transparent also heated it, suppressing the formation of small galaxies in low-mass halos. The cosmic web, as it exists today, is a product of this history. The structure of the filaments and voids, the warm-hot intergalactic medium in the filaments, the temperature and ionization state of the gas in the voids, all of it was set in part by the reionization process. The space between galaxies today is warm and ionized because the earliest galaxies and quasars lit up and changed it. Let's talk about the 21 centimeter signal and what it might tell us. Neutral hydrogen, even in the Dark Ages and the early stages of reionization, emits radio waves at a very specific wavelength. When the electron in a hydrogen atom flips its spin from the same orientation as the proton to the opposite orientation, it releases a photon with a wavelength of 21 centimeters. This 21 centimeter signal was present throughout the cosmic Dark Ages, emitted by the neutral hydrogen fog that filled the universe before the first stars formed. Because the universe has expanded since then, that original 21 centimeter signal has been stretched to much longer wavelengths, into the meter wavelength radio range. Radio telescopes sensitive to those wavelengths, listening in the directions that correspond to specific epochs during the cosmic Dark Ages and reionization, could in principle detect the 21 centimeter signal from that neutral hydrogen. Mapping the 21 centimeter signal across the sky would give an image of the neutral hydrogen distribution at the epoch of reionization, a direct picture of those first bubbles of ionized gas expanding around the first stars and quasars. No telescope yet built has achieved this. The cosmic 21 centimeter signal is very faint, and radio frequency interference from Earth technology, particularly from FM radio and digital TV transmitters, overlaps with the wavelengths of interest. The hydrogen epoch of reionization array in South Africa and the SKA telescope array under construction in South Africa and Australia are among the instruments working toward this detection. If successful, they will give us the most direct image of cosmic dawn we can achieve, a map of the universe at a time when the first galaxies were carving ionized bubbles in the neutral intergalactic fog. Tonight, we're going to sit with what that history means for the space between galaxies as we see it today. The intergalactic medium, the warm hot gas in the filaments, the cool ionized plasma in the voids, the thin fog of heavy elements carried out of galaxies on stellar winds, is not a remnant of some pristine primordial state. It is the processed, heated, ionized, chemically enriched product of 13 billion years of galaxy evolution. Every cubic meter of intergalactic space, with its average of 1 proton, has been touched by the radiation and the outflows of countless generations of stars. The distances between galaxies are not just spatial, they contain a history. The light that crosses them carries in its wavelengths the story of what those distances were filled with at every epoch of the universe's past. And we can read that story in quasar spectra and 21 centimeter maps and X-ray observations of WIM filaments, in enough detail to reconstruct the history of the universe between the galaxies, not just inside them. That is perhaps the most extraordinary thing about looking across intergalactic distances. We are not just measuring how far away things are. We are reading the autobiography of the universe, written in the light that has crossed the spaces between its galaxies for billions of years and only now arrived at our eyes. Tonight, we're going to talk about what fills the space between galaxies, because the answer is not nothing, it is almost nothing, and the distinction matters more than it might seem. The intergalactic medium is the term astronomers use for the diffuse gas that occupies the space between galaxies. It is composed primarily of hydrogen and helium in an ionized state, meaning the electrons have been stripped from the atomic nuclei by the radiation of the first stars and quasars a few 100 million years after the Big Bang. It is thin beyond almost any comparison we can make. Let's talk about how thin. A cubic meter of the air you are breathing right now contains roughly 25 quadrillion molecules. 25, followed by 15 zeros. A cubic meter of the best vacuum we can create in a laboratory contains perhaps a few billion molecules, down from that quadrillion scale number, but still enormous by intergalactic standards. A cubic meter of the intergalactic medium contains, on average, about 1 proton. 1. A single hydrogen nucleus per cubic meter of space. If you stretched your arms out and rotated slowly, you would describe a sphere roughly 1.5 meters in diameter. Inside that sphere of empty-seeming air there are about 40 quadrillion molecules. Inside an equivalent sphere carved out of the intergalactic medium, there would be less than 1 proton on average. The intergalactic medium is not a physical barrier in any sense that your body would register. It is nearly nothing. It is also one of the largest bodies of matter in the observable universe, because if you multiply 1 proton per cubic meter by the volume of the observable universe, the total comes to an enormous amount of hydrogen and helium, more than exists in all the stars and galaxies combined. Most of the normal matter in the universe is not in stars. It is not in planets. It is not in galaxies at all. It is spread thinly across the vast spaces between them. But the intergalactic medium is not uniform. It is structured in ways that trace the cosmic web, where filaments of the web connect galaxy clusters. The intergalactic medium is slightly denser and hotter, what astronomers call the warm-hot intergalactic medium. In the centers of galaxy clusters, the medium is denser still, millions of degrees Kelvin, emitting X-rays that we can detect from Earth. In the voids, the medium is at its most dilute, as close to true emptiness as the universe gets outside of certain exotic theoretical scenarios. Now, let's talk about expansion, because this is where the distances between galaxies become something even harder to process than simple scale. In 1929, Edwin Hubble published measurements showing that the light from distant galaxies was systematically shifted toward the red end of the spectrum, and that the farther a galaxy was, the more shifted its light appeared. The interpretation, which became one of the most confirmed facts in all of science, is that the universe is expanding. Every galaxy cluster is moving away from every other galaxy cluster. The universe is not a fixed container with things moving inside it. The container itself is getting larger. Here is the key distinction that changes everything. The galaxies are not moving through space like shrapnel from an explosion. Space itself is expanding between them. The metric of the universe is stretching. If you marked 2 points in the intergalactic medium and came back 1 billion years later, those 2 points would be farther apart, not because anything moved, but because the space between them grew. This means that the recession speed of distant galaxies is not limited by the speed of light in the same way that the motion of objects through space is. A galaxy 1 megaparsec away appears to recede at about 43 miles per second due to expansion. A galaxy 10 megaparsecs away recedes at about 435 miles per second. A galaxy far enough away recedes at the speed of light. Beyond that critical distance, the recession speed exceeds the speed of light, and light from those galaxies can never reach us. No one expects that critical distance to imply what it does. No one predicts, when they first encounter the expanding universe, that there are galaxies existing right now that we will never be able to observe, not because they are behind something, but because space is expanding between us faster than light can cross it. Absolutely no one anticipates the particular loneliness this implies, that the observable universe is not the whole universe, but a bubble defined by the speed of light against the rate of cosmic expansion. Let's talk about the practical scale of this. The Hubble constant, which measures the rate at which space expands per unit distance, is estimated at roughly 42 to 46 miles per second per megaparsec, depending on the measurement method. The discrepancy between those two values is known as the Hubble tension, one of the most significant unresolved problems in modern cosmology, and we will return to it. But taking the average, the expansion rate means that for every megaparsec of distance, roughly 3.26 million light-years, 2 points in space are moving apart at about 43 miles per second. At roughly 4,300 megaparsecs from Earth, the recession speed due to expansion reaches the speed of light. This is the Hubble radius, about 14 billion light-years. Beyond this distance, light from a galaxy cannot reach us unless the universe slows its expansion significantly. Our current models predict that the expansion is not slowing, it is accelerating. This is what dark energy means in practical terms. Not a mysterious force pulling things apart, but a property of space itself that causes the expansion to speed up over time. As expansion accelerates, the radius within which galaxies can still communicate with us shrinks. Galaxies that are now near the edge of the observable universe are slowly, over billions of years, being pushed beyond the point where their light can reach us. They will not disappear instantly, but they will redshift progressively, their light stretched to longer and longer wavelengths, eventually to radio waves, then to waves too long to detect, then to silence. The gaps between galaxies are not stable features of the universe. They are widening. By the end of tonight, we will sit with what that means on the very longest timescales. We have talked about the intergalactic medium as the near nothing that fills the space between galaxies. But the story of the intergalactic medium has a specific problem at its heart that was, for decades, one of the most embarrassing discrepancies in cosmology, the problem of the missing baryons. Let's talk about what baryons are and why they went missing. Baryons are the particles that make up ordinary matter as we experience it. Protons and neutrons, the building blocks of atomic nuclei, the stuff of stars and planets and people. In the early universe, the ratio of baryons to photons and the total density of baryons relative to the critical density of the universe can be calculated precisely from the temperature fluctuations in the cosmic microwave background. The calculation gives a definitive number. The universe should contain a certain amount of ordinary baryonic matter. When cosmologists in the 1990s and early 2000s added up all the baryons they could find, in stars, in galaxies, in the cool gas of molecular clouds, in the hot gas in galaxy clusters visible in X-rays, they came up short, not by a small amount, by roughly half. Only about half of the baryons predicted by the Big Bang model appeared to be accounted for in observations. The other half were missing. No one expects half the normal matter in the universe to be unaccounted for. No one predicts, when doing careful census work on galaxies and their gas, that the result will be missing half the budget. Nobody anticipates that the missing matter would turn out to have been hiding for decades in the intergalactic medium all along. The theoretical prediction was that the missing baryons should be in the form of warm-hot intergalactic medium, a diffuse, highly ionized gas at temperatures between 100,000 and 10 million Kelvin, permeating the cosmic web filaments and the outskirts of galaxy clusters. At those temperatures, the gas emits primarily in the soft X-ray and far ultraviolet wavelength ranges, which are extremely difficult to detect because Earth's atmosphere absorbs X-rays and the telescopes capable of far UV detection are expensive and rare. The observational confirmation of the warm-hot intergalactic medium came gradually. Absorption features in the spectra of distant quasars, narrow lines corresponding to oxygen and neon ionized by the extreme temperatures of the WHM, began to accumulate in X-ray observations from the Chandra and XMM Newton space observatories. By the late 2010s, the case for the WIM as the reservoir of the missing baryons was strong enough to be broadly accepted. The 2020s have seen further refinements, including direct emission detections in some of the densest filaments. The implication for the intergalactic distances is this: the space between galaxy clusters is not as empty as it appears. It contains a diffuse gas, the warm-hot intergalactic medium, that accounts for roughly 40 to 50% of all the normal matter in the universe. If you could somehow visualize the baryonic content of the universe, not just the stars and galaxies that emit visible light, but all the normal matter, you would see the filaments of the cosmic web glowing in soft X-rays, a faint bridge of warm plasma connecting the galaxy clusters at the nodes. This bridge of gas is relevant to another phenomenon: the feedback between galaxies and their surrounding medium. Let's talk about how galaxies communicate with the intergalactic medium. Galaxies are not sealed systems. They constantly exchange material with the medium around them. When supernovae explode in large numbers, as they do in galaxies with high star formation rates, they drive outflows. Gas is pushed out of the galaxy at hundreds of miles per second, escaping into the intergalactic medium. This outflowing gas carries with it heavy elements synthesized in the cores of stars and dispersed in supernova explosions. Carbon, oxygen, iron, silicon, all the elements beyond hydrogen and helium that make chemistry and life possible, are blown out of galaxies and into the intergalactic medium over billions of years. The intergalactic medium between galaxies is therefore not pristine hydrogen and helium from the Big Bang. It is metal enriched. It contains the processed output of billions of years of stellar evolution, carried out of galaxies on galactic winds. When astronomers observe the spectra of distant quasars, looking at absorption lines from the gas between us and the quasar, they see the signatures of these heavy elements in the intergalactic medium at distances corresponding to all epochs of cosmic history. In return, the intergalactic medium is a reservoir from which galaxies can draw fresh gas for future star formation. Cosmological simulations show galaxies accreting gas from the surrounding medium along filamentary streams that penetrate the hot halo surrounding the galaxy. This cold mode accretion, as it is called, is thought to be the dominant way that large galaxies maintain their supply of star-forming gas over cosmic time. Before we get started on the next part of this picture, consider what this exchange means for the intergalactic gaps in a broader sense. They are not passive. They are active participants in the evolution of galaxies. The gas that was in a star in the Milky Way 10 billion years ago may have been blown out in a galactic wind, drifted through the intergalactic medium for billions of years, and been accreted back into a galaxy somewhere else. The matter in the universe circulates on scales measured in millions of light years, on timescales measured in billions of years, in a cycle that connects the interiors of galaxies to the vast emptiness between them. The distance between galaxies from this perspective is not the boundary of a closed system. It is the length of a pipe. Matter flows through the pipe, slowly, carried by gravity and galactic winds and the expansion of space. The galaxies at either end are connected to it, drawing from it and contributing to it, over timescales that dwarf human civilization, by factors so large they lose meaning. And the Lyman alpha forest, the pattern of absorption lines in quasar spectra that traces the intergalactic hydrogen at all redshifts, is one of the most precise tools cosmologists have for measuring the large-scale structure of the universe and the history of its expansion. It is a map of the pipes between the galaxies, drawn in the spectra of distant beacons. The intergalactic medium is not nothing. It is the connective tissue of the universe. It just happens to be so thin that crossing it from one side to the other would take longer than the current age of the cosmos, even at the speed of light. Tonight, we're going to talk about the most important boundary in the universe. Not a physical wall, not a barrier made of matter. A boundary defined entirely by the relationship between the speed of light and the age of the cosmos, the edge of the observable universe. Let's talk about what it means that the observable universe has an edge at all. The universe was born roughly 13.8 billion years ago. Since then, light has been traveling through it. The maximum distance that light could theoretically have traveled in 13.8 billion years in a static universe would be about 13.8 billion light years. But the universe has been expanding the whole time, which means that the regions of space that emitted the oldest light we can detect have moved farther away from us during the journey of that light. When you account for the expansion, the furthest observable distance, the radius of the observable universe, turns out to be about 46 billion light years. 46 billion light years in every direction. A sphere of observable space with Earth near the center. This is not a special position. Every observer in every galaxy would see a similar sphere centered on themselves. the observable universe is not a fixed region of space. It is a personal horizon, defined by the age of the cosmos and the history of its expansion. But what lies beyond that 46 billion light-year boundary? Almost certainly more universe, probably much more. The observable universe is the portion we can see, not the whole of what exists. Current measurements of the geometry of space suggest that the universe is very close to spatially flat, which in the mathematics of cosmology points toward a universe much larger than the observable sphere, and possibly infinite. If the universe is infinite, then the matter and galaxies and structures we see within our 46 billion light-year bubble are simply a finite sample of an infinite distribution. Our observable bubble is, in that case, a horizon imposed by time, not a wall imposed by space. No one expects the boundary between observable and unobservable to feel as significant as it does when you sit with it. No one predicts, when they first learn that the universe may be infinite, the particular quality of the strangeness this implies. Nobody anticipates the sense that what we call the universe, the observable sphere of 46 billion light-years, may be cosmically local, a neighborhood that does not contain even the closest galaxies beyond our horizon, let alone anything representative of the total structure. Let's talk about what this means for the future of the distances between galaxies. In the very far future, the acceleration of expansion will do something that has no historical precedent and no everyday analog. It will make parts of the present universe permanently inaccessible, not just difficult to reach, but impossible to ever hear from again. The acceleration means that galaxies currently within the observable universe but far away from us will eventually be receding faster than light. Their light will never reach us again. They will cross our cosmic event horizon and vanish from all possible observation. The galaxies that will survive in our observable universe indefinitely are only those gravitationally bound to the local group. Andromeda and the Milky Way will merge in about 4.5 billion years. The Triangulum galaxy and a few dwarf companions will also remain. Everything beyond the local group, the Virgo cluster, Laniakea, every other supercluster, every other galaxy in the observable universe today, will eventually cross the event horizon and disappear, not by moving, not by being destroyed, by the expanding universe pushing them beyond the reach of any signal we could send or receive. In roughly 100 billion years, a civilization living in the merged Milky Way Andromeda galaxy will look out at a sky almost entirely empty of external galaxies. The cosmic microwave background will have redshifted to wavelengths too long to detect. The evidence for the Big Bang will be essentially gone. The evidence for the cosmic web will be gone. Evidence for almost anything beyond the local group will be gone. That civilization, equipped with instruments as good as our own, will have almost no way of knowing that the universe was once full of hundreds of billions of galaxies. They will face the universe we face, but without even the clues we have. Let's talk about what the intergalactic distances mean in this context. Tonight, we have walked from the distance to Andromeda, 2.5 million light-years, to the structure of the local group, to the Virgo cluster, to Laniakea, to the cosmic web, to the voids. We have looked at what fills the spaces between galaxies and at how those spaces are growing. But here is the thing that quietly sits underneath all of this. The universe contains an estimated 2 trillion galaxies, 2 trillion islands of stars, and the vast majority of the space between them is, by any meaningful measure, empty. If you were to fill the observable universe with stars at the same density as the interior of the Milky Way, the universe would be almost incomprehensibly bright, but that is not what the universe is. The universe chose through the action of gravity over cosmic time, to gather all of its matter into a tiny fraction of its volume, and to leave the rest empty. The distances between galaxies are worse than you think, not because of any particular number, but because of what those numbers imply collectively. They imply that the universe is not a crowded place. It is an empty place with occasional isolated bright spots. The bright spots are extraordinary, but they are the exception. Silence and darkness, and the near absolute void of intergalactic space are the rule. No one expects that to be the case when they first encounter the night sky, glittering with thousands of visible stars. No one predicts that a sky full of light is actually showing us the interior of one small province of one small galaxy, and that beyond the edge of that galaxy lies a vastness that makes the galaxy itself look negligible. It comes as a genuine surprise that, until they have sat with the numbers long enough, that the universe we live in is mostly nothing, interrupted occasionally by something, and that the something, for all its wonder, does not fill even a measurable fraction of the total volume. By the end of tonight, we will sit with what that means for us as observers, as the only species we know of that has looked up and measured the size of the silence it lives inside. Tonight we're going to talk about what the acceleration of expansion means on the very longest timescales, because it is on those timescales that the distances between galaxies reveal their most important implication. Not just how far things are now, but how isolated everything will eventually become. Tonight, we're going to talk about the concept of the cosmic event horizon. The Hubble radius is the distance at which, right now, galaxies are receding from us at the speed of light due to expansion. Currently, that sits at about 14 billion light years. Beyond that distance, light cannot make progress toward us against the expansion. But the Hubble radius is not fixed. As the universe expands and the expansion rate changes, the Hubble radius changes. The cosmic event horizon is different. It is the maximum distance from which a signal emitted now could ever reach us in the future, given the way expansion is expected to accelerate. Because dark energy is causing expansion to accelerate, the cosmic event horizon is finite. Signals from galaxies beyond roughly 16 billion light-years emitted today will never reach us. We can still see those galaxies now because light they emitted in the past, when the universe was smaller and expansion was slower, has already been in transit long enough to arrive. But the light they emit today will never catch up. No one expects this to feel quite as vertiginous as it does. No one predicts, when they first understand cosmic expansion, that some galaxies we can currently see are already beyond the range of any future contact. We can observe them. We can study the ancient light that has already arrived. But if we tried to send a signal to those galaxies today, it would never arrive. We are watching things we can never speak to. Let's talk about what this means over the very long future. As time passes and expansion accelerates, galaxies that are currently within the cosmic event horizon will drift beyond it. Their light will be progressively redshifted to longer and longer wavelengths, dimmer and dimmer, as the expanding space between us and them stretches the light. Eventually, their light will be redshifted to wavelengths too long to detect with any physically realizable instrument. They will disappear from any possible observation, not because they have been destroyed, but because the space between us and them has expanded to a point where their photons cannot traverse it. In roughly 100 billion years, a time that is about 7 times the current age of the universe, the only galaxies remaining within the observable horizon of the Milky Way will be those gravitationally bound to the local group. Andromeda and the Milky Way will by then have merged into Andromeda. A few dwarf companions will also remain. Everything else, the Virgo cluster, the Perseus cluster, the Coma Supercluster, the Shapley Supercluster, will have faded below detectability. The universe will look entirely different to observers in that era, if any exist. They will see a sky full of stars within Andromeda, and beyond the edges of their galaxy, nothing. No other galaxies visible to the naked eye. No bright patches in the sky corresponding to nearby galaxy clusters. No smudge in the direction of Andromeda, because Andromeda will be their own galaxy. No evidence of the cosmic web. No evidence that hundreds of billions of other galaxies ever existed. Few cosmologists anticipate, when first thinking about a universe of 2 trillion galaxies, that such a universe could become observationally indistinguishable from a universe containing only one galaxy. But that is what the acceleration of expansion appears to guarantee, given enough time. Let's talk about what we lose as the distances grow. One of the most important things we lose, in the cosmological future, is the ability to determine whether dark energy exists and what it does. The evidence for dark energy comes primarily from observations of distant type Ia supernovae and the cosmic microwave background. Both of those evidence streams require access to the wider universe. In the far future, when the wider universe has drifted beyond the horizon, both will be unavailable. The CMB will have redshifted to wavelengths too long to detect. Distant supernovae will be inaccessible. Future observers will have no way to measure the expansion history of the universe and no way to infer the presence of dark energy. The cosmological model that we have painstakingly built over the last century, the knowledge that the universe is expanding and accelerating, that it began 13.8 billion years ago, that it contains dark matter and dark energy, that it emerged from a hot, dense state, will all be inaccessible to observers living in the distant future. They will begin with a completely different set of facts. Their night sky will show nothing beyond their own merged galaxy. Their measurements will yield a universe that appears static, bounded, and alone. This is not a scenario in the far future for some alien civilization. It is, in a sense, the terminal state of the information available to any observer in this universe. We live at a privileged moment, when the cosmic web is still visible, when the expansion history can still be read from the sky, when the evidence for the Big Bang is still present in the microwave background. We live in the era when the full picture is available, and that era is finite. No one expects the privilege of our current cosmological moment to feel as significant as this reframe makes it. We take for granted the 2 trillion galaxies visible in our sky, the evidence of the Big Bang in every direction, the cosmic web mapped across billions of light years. But all of that is time-limited. The universe is keeping the evidence available for a fraction of its total lifespan, and we happen to be alive in that fraction. Let's talk about what comes after the isolation is complete. After the local group has merged into Andromeda and everything else has crossed the event horizon, the universe continues. The stars of Andromeda continue to age and die. The massive ones explode as supernovae and leave neutron stars and black holes. The smaller ones cool slowly over trillions of years. The gas available for new star formation is gradually consumed, and the rate of star formation declines. After a few trillion years, the last generation of stars, red dwarfs burning hydrogen slowly at low temperatures, exhaust their fuel and cool to black dwarfs. No new stars form. At this point, the universe's visible content is reduced to black dwarfs, neutron stars, black holes, and a diffuse remnant of the intergalactic medium, now spread even more thinly across a vastly larger volume of space. The distances between things, already enormous, have grown by orders of magnitude due to continued expansion. The process continues on timescales that dwarf anything we have considered tonight. Protons, if the current best models are correct, may eventually decay, dissolving atomic matter into photons and lighter particles over timescales of around 10 to the power of 34 years. Black holes evaporate via Hawking radiation on timescales that, for the largest known black holes, approach 10 to the power of 100 years. After all of that, the universe may reach a state cosmologists call the heat death, a state of maximum entropy where no further thermodynamic work is possible and no structures of any kind remain. The intergalactic distances will not be crossed by that point. They will be meaningless. There will be nothing at either end to do the crossing. Tonight we're going to let that thought settle, not as horror, but as scale. Not as an ending, but as a measure of the extraordinary fact that anything exists at all, that the universe chose to organize some of its matter into galaxies and stars and planets and observers who could look out and measure the distances between things and know, for a brief window in cosmic time, what kind of universe they live in. By the end of tonight, we are going to ask the question that has been underneath everything we have discussed. Given what the distances between galaxies actually are, could anything, any civilization at any level of technology, ever cross them? And if not, what does that mean for the question of whether we are alone? Tonight, we're going to talk about what intergalactic travel actually requires. The distance to Andromeda is 2.5 million light-years. Even at the speed of light, the theoretical maximum speed in the universe, crossing that distance would take 2.5 million years. Not in the reference frame of a hypothetical photon, which experiences no time at all, but in the reference frame of Earth and Andromeda, 2.5 million years would pass. Any civilization sending a message or a probe at the speed of light to Andromeda would need to wait 5 million years for a round trip. Any civilization attempting to visit Andromeda and return would need either extraordinary lifespans, generational ships, or some form of suspended animation lasting millions of years. And Andromeda, as we have established, is the nearest large galaxy. The nearest galaxy in any direction outside the local group is the Canis Major Dwarf at about 25,000 light-years, but it is a disrupted dwarf being cannibalized by the Milky Way and arguably part of the Milky Way system. The nearest genuinely separate galaxy is the Canis Major Overdensity, or possibly Segway 1, both within 100,000 light-years. Beyond the local group, the nearest external system outside our gravitationally bound neighborhood is the Maffei group, at about 9.8 million light-years. Even with propulsion systems that could reach a significant fraction of the speed of light, something vastly beyond current or foreseeable technology, crossing from one galaxy cluster to another would require travel times measured in millions of years. The distances are not just large. They are large relative to the speed of light in a way that places them in a fundamentally different category from any engineering challenge involving distance. No one expects the phrase intergalactic travel to describe something categorically impossible at any foreseeable level of technology. No one predicts, when they hear the word starship, that the scales being discussed eventually become incompatible with any plausible biological or technological timeline. But the intergalactic distances suggest exactly this. Within a galaxy, very advanced technology might permit travel between stars on timescales of decades or centuries at high fractions of light speed. Between galaxy clusters, even at the speed of light, the timescales become millions of years. Now let's add expansion. The recession of distant galaxy clusters due to expansion means that a probe sent toward the Virgo cluster 54 million light-years away, would need to fight against an expanding space the whole way there. Depending on the expansion rate and how it changes over time, there is a threshold distance beyond which a probe traveling at the speed of light cannot make progress. Even traveling at the maximum possible speed, the expansion of space between the probe and its destination would outpace the probe's advance. There are galaxy clusters visible in today's sky that cannot be reached by any probe, no matter how fast, sent from Earth today. The distances between us and those clusters are growing faster than light can cross them. This is the intergalactic travel problem in its starkest form. Not just that the distances are large, but that some of them are unbridgeable in principle, not merely in practice. Let's talk about what this means for the Fermi paradox. The Fermi paradox asks, if intelligent life is common in the universe, why do we not detect signals from it? The universe is large and old and contains 2 trillion galaxies, each with hundreds of billions of stars. Even if intelligent life is rare by any reasonable estimate, the sheer number of candidate locations suggests there should be many civilizations out there. Where are they? The standard responses to the Fermi paradox involve everything from the possibility that life is rarer than we think, to the possibility that intelligent life tends to destroy itself before developing the technology to communicate at interstellar distances, to the possibility that civilizations exist but are not broadcasting in ways we can detect. The intergalactic distances add a dimension to this that is sometimes underappreciated. Most discussions of the Fermi paradox implicitly assume that a sufficiently advanced civilization could span its galaxy. Within a single galaxy, relativistic travel or long-duration generational ships might permit a civilization to colonize other star systems over millions of years. But between galaxy clusters, the paradox shifts. A civilization in Andromeda could colonize every star system in Andromeda without being able to make meaningful contact with anyone in the Milky Way on any reasonable timescale. The intergalactic gap is not just a communications lag. It is, for any civilization limited by physics as we understand it, a permanent separation. If we someday receive a signal from a civilization in Andromeda, that signal would have left Andromeda 2.5 million years ago. The civilization that sent it may no longer exist. Our reply, sent at the speed of light, would arrive 2.5 million years in Andromeda's future. The exchange we could conduct in a single human lifetime would span 5 million years of cosmic time on Andromeda's end. Whatever question we asked and whatever answer eventually came back, neither party would share a coherent present moment. Almost nobody anticipates, in the early decades of SETI, how thoroughly the geometry of the universe limits what any kind of first contact could mean. No one predicts that even a positive result, even a verified signal from another civilization in another galaxy, would come with the caveat that the civilization that sent it existed millions of years ago and may be long extinct. The universe is old enough and large enough that every signal from outside the local group is, in a sense, a fossil, evidence of something that was, not necessarily of something that still is. Now let's talk about one more implication. If intelligent civilizations do exist in other galaxy clusters, they face the same expanding universe we face. They too live in a bubble defined by the cosmic event horizon. They too are watching the rest of the universe slowly drift beyond the range of any possible signal or probe. In 100 billion years, if any civilization survives that long, they will be as isolated as we discussed earlier, unable to see evidence of any other cluster, unable to know whether they are alone. But here is something worth sitting with. We exist right now. in the era when the full observable universe is still available, when the cosmic web is still visible, when the light from 2 trillion galaxies is still reaching us and can be measured and analyzed and turned into the kind of understanding that lets us have conversations like this one. By the end of tonight, you understand what the distances between galaxies actually mean. Not just the numbers, the implications, the isolation of each cluster, the impermanence of the view, the extraordinary specificity of being here in this galaxy, in this era, with instruments sensitive enough to see the web and smart enough to understand what we are seeing. The universe did not have to be this legible, but for a moment, from where we sit, it is. Tonight we're going to talk about what the James Webb Space Telescope has revealed about the early universe, because in the few years since it became operational, it has changed what we thought we understood about intergalactic distances in the most unexpected way. It has not changed the distances themselves. It has changed what we thought existed at those distances. Let's talk about what JWST was designed to see. The James Webb Space Telescope was launched in December 2021 and reached its operational position at the L2 Lagrange point, about 1 million miles from Earth in the direction away from the Sun, in January 2022. Unlike the Hubble Space Telescope, which observes primarily invisible and ultraviolet light, Webb is optimized for infrared wavelengths. This is crucial for looking at the early universe, because light from the most distant, youngest galaxies has been redshifted by the expansion of space to infrared wavelengths by the time it reaches us. Hubble could see to a certain depth. Webb could see farther, to the first few 100 million years after the Big Bang. What astronomers expected to find at those extreme distances, at redshifts of 7, 8, 10 and higher, were the seeds of galaxies, the early building blocks, small, irregular collections of young stars, barely beginning to assemble into what would eventually become the mature spirals and ellipticals of the present universe. The leading cosmological model, Lambda CDM, made clear predictions about this. Small structures form first. They merge over time to build larger structures. The galaxies of the early universe should be small and immature. No one expected what Webb actually found. In its first year of science operations, Webb identified galaxy candidates at extreme redshifts, corresponding to distances of over 30 billion light-years and epochs less than 400 million years after the Big Bang, that were not small and immature. They were massive. The stellar masses inferred from their light implied that some of these early galaxies had already assembled as much mass as the Milky Way contains today, or more, within the first 5 to 10% of the universe's lifetime. In April 2023, a team led by Michael Boylan-Kolchin published a paper in Nature Astronomy arguing that 6 of the JWST galaxy candidates, if confirmed, would be too massive to exist, given the standard model of cosmology. Their presence would challenge the fundamental understanding of how quickly matter could have assembled into stars and galaxies in the early universe. Absolutely no one anticipated this. No one predicted that the telescope designed to confirm our picture of early galaxy formation would instead find what appeared to be mature galaxies where only protogalactic fragments should exist. The results sparked intense debate. Some researchers argued that the mass estimates were too high, that systematic errors in the photometric redshift measurements were making the galaxies appear more massive than they were. Others argued that the detections were real and implied that star formation in the early universe was faster and more efficient than any current model predicts. By 2024, spectroscopic follow-ups had confirmed several of the most extreme candidates. The galaxies were real. Their redshifts were real. some of their implied masses remain genuinely challenging for the standard model. The cosmological community is currently in the process of revising early galaxy formation models to account for what Webb has found. But what does this have to do with intergalactic distances? The distance to these early galaxies, roughly 30 billion light-years or more, is at the edge of what the observable universe contains. These are among the most distant objects we have ever observed. And what we are seeing at those distances is not what we expected. The implication is that the universe, even at its most remote and ancient observable depths, is already doing things that surprise us. Before we get started on what this means, consider what it says about how we use distance as a tool for understanding the universe. Every photon that reaches Webb from a galaxy 30 billion light-years away has been traveling for more than 13 billion years. The information it carries is a snapshot of the universe at a very specific moment in the past. When that snapshot does not match our predictions, we have to go back and ask what was happening in the space between then and now that our models got wrong. The intergalactic distances in this context are not just separations between things. They are also separations in time. Each distance corresponds to a look-back time, a window into the past. When we look across intergalactic distances, we are simultaneously exploring cosmic geography and cosmic history. And the history that Webb is revealing is less ordered, less predictable, and more extreme than we thought. Let's talk about what JWST has found closer to home as well. At smaller distances, Webb has also been measuring Cepheid variables in nearby galaxies with a precision that was not possible before. The goal was to provide a more accurate anchor for the cosmic distance ladder and help resolve the Hubble tension. The early Webb Cepheid results, published in 2023 by Adam Rees and collaborators, confirmed the Hubble tension rather than resolving it. The local expansion rate measured with Webb-calibrated Cepheids and type Ia supernovae remains stubbornly at around 45 miles per second per megaparsec, inconsistent with the CMB-derived value of about 67. The implication is that the tension is a genuine feature of the cosmological data, not an artifact of the older instruments used to measure it. The most likely explanation, if systematic errors can be ruled out, is new physics, something in the early universe or in the nature of dark energy that the standard model does not capture. The resolution, if and when it comes, may change how we calculate intergalactic distances and how fast the universe between galaxies is growing. But for now, the Hubble tension stands as one of the most important open questions in cosmology, and JWST, rather than resolving it, has made the mystery harder to dismiss. Tonight we're going to sit with that uncertainty as part of what the distances between galaxies mean. Not a clean picture with agreed upon numbers, but a picture still being refined, still surprising, still yielding results that force us to revise what we thought we knew about the larger scales of the universe. Tonight, we're going to talk about something that most descriptions of the cosmic web leave out. The Milky Way is not sitting still in the middle of the local group, patiently waiting for the universe to expand around it. It is moving. The entire local group is moving, and the direction it is moving toward tells us something remarkable about the large-scale structure of everything around us. Let's talk about peculiar velocity and the great attractor. Every galaxy in the universe has two components to its apparent motion relative to us. The first is the Hubble flow, the recession velocity caused by the expansion of space itself. The second is what astronomers call the peculiar velocity, the actual motion of the galaxy through space relative to the expanding frame. Peculiar velocities arise from gravitational interactions with nearby mass concentrations. every galaxy is being pulled by the gravity of all the other mass around it, and those pulls add up to a net velocity that can be measured. The cosmic microwave background gives us a reference frame for the universe as a whole, and measurements of the CMB dipole, the slight temperature asymmetry between opposite directions of the sky caused by our own motion through the CMB frame, tell us that the local group is moving at roughly 390 miles per second toward a region of the sky in the direction of the constellations Hydra and Centaurus. 390 miles per second, not because of expansion, because something out there has enough gravity to pull us. And for decades, astronomers did not know what it was. The mystery deepened in the 1970s and 1980s as surveys of the distribution of galaxies and clusters in our general vicinity revealed that not just the local group, but essentially everything within several 100 million light-years seemed to be streaming toward the same general region. The Virgo cluster contributed some pull, but even accounting for Virgo, there was an excess. Something hidden behind the dense gas and dust of the Milky Way's disk that blocks optical observations in that direction was pulling half the local universe toward it. The object responsible became known as the Great Attractor. Subsequent surveys in radio, X-ray, and near-infrared wavelengths, which can penetrate the Milky Way's obscuring disk better than optical telescopes, eventually revealed the answer. The primary mass responsible was the Norma cluster, a rich galaxy cluster about 220 million light-years away, embedded in the larger Norma supercluster. But even the Norma cluster turned out not to be the full story. Further analysis revealed that the mass pulling on us extends well beyond the Norma cluster, to a structure that includes the Hydra-Centaurus supercluster and possibly the enormous Shapley concentration, a dense supercluster complex about 650 million light-years away that contains so much mass it influences the motions of galaxies across hundreds of millions of light-years. No one expects, when first mapping the local universe, that the structure of the cosmic web would be directly felt as a physical pull on our own galaxy. No one predicts that the pattern of galaxy distribution visible in a telescope survey would correspond to a measurable acceleration of the entire local group. It is hard to anticipate that the peculiar velocity of the Milky Way would turn out to be a direct measurement of the mass distribution of the cosmic web in our neighborhood. Let's talk about what this motion means for the intergalactic distances. The peculiar velocity of the local group introduces an asymmetry into our view of the universe. The galaxies we see in the direction of the Great Attractor appear to be receding from us slightly more slowly than the Hubble flow alone would predict, because we are moving toward them. The galaxies in the opposite direction appear to be receding slightly faster. This asymmetry is measurable and must be accounted for in any precise determination of the Hubble constant from local measurements. More importantly, the existence of large-scale flows, coherent motions of galaxy clusters across hundreds of millions of light-years, tells us something about the distribution of mass in the universe on the largest accessible scales. Those flows are gravitational measurements. By mapping how everything is moving, astronomers can infer where the mass is, including the dark matter that is invisible to direct observation. This is how the 2014 Laniakea mapping by Brent Tully and colleagues worked. They measured the velocities of thousands of galaxies and traced the flow lines back to the basin of attraction. The volume of space whose gravitational influence shaped those velocities. Laniakea is defined not by the positions of galaxies, but by the pattern of cosmic flow, the large-scale motion of matter toward a common center. Our motion toward the Great Attractor is, in this sense, a feature of the cosmic web. We are flowing along a filament of the web toward the dense node where the Shapley concentration anchors the flow. The same process that built the filaments over billions of years is still happening. Matter is still flowing from voids into filaments, from filaments into clusters, from smaller clusters into larger ones. The cosmic web is not a static structure. It is a dynamic flow, and we are embedded in it, being pulled slowly along by gravity towards structures hundreds of millions of light years away. Before we get started on the final picture, let's hold that image for a moment. The Milky Way, moving at 390 miles per second through space. The local group, following it. Laniakea, itself a basin of attraction for hundreds of galaxy groups, streaming toward an even larger attractor. Layer upon layer of gravitational influence, each pulling on the next, the whole web in slow motion toward the densest nodes in its own structure. The distances between galaxies, enormous as they are not unchanging. They are the arena in which gravity plays out over cosmic time, and everything inside that arena is in motion. Tonight, we're going to let that picture settle into the full scale of what we have explored. The distances between galaxies, the voids, the filaments, the cosmic horizon, the intergalactic medium, the reionization of the universe, the peculiar velocities, the expanding space, the isolated future. Each of these is a layer of the same story. The story of a universe that began in a state of near-perfect uniformity and spent 13.8 billion years organizing itself into the specific landscape we find ourselves inside tonight. We began tonight with something familiar, the nearest large galaxy to our own, 2.5 million light-years away, faintly visible on a clear night as a smudge of ancient light that left its source before our species existed, and we have walked from there to the local group, to the Virgo cluster and Laniakea, through the filaments and voids of the cosmic web, into the near emptiness of the intergalactic medium, through the mechanics of an expanding universe, and finally to the edge of what we can observe and what lies permanently beyond it. What we have found each time we scaled up is that the universe becomes emptier than we expected. The local group is a small gathering in a much larger void. The Virgo Supercluster is one lobe of a much larger structure. Laniakea itself sits in an underdense region of the cosmic web, and the cosmic web, for all its extraordinary filaments and galaxy-rich nodes, is mostly not filament and not node. It is void, vast, deepening, ancient absence. The distances between galaxies are worse than you think because of what they imply about where we are in the structure of everything. Not at the crowded center of a dense cluster, not in the bright heart of a filament, but in the quiet interior of an underdense region, in a small cluster of galaxies bound together by gravity, watching the rest of the universe expand away from us at ever-increasing speeds, with most of the story of the cosmos already receding beyond the reach of any signal we could send or receive. There is a strange kind of clarity that comes from sitting with that. Not despair, not smallness in any diminishing sense, but an awareness of context that most of the universe's history has not had the benefit of having. We are the matter that became curious about itself. We are the universe measuring its own distances, feeling its own loneliness, naming its own voids, discovering its own boundaries. The intergalactic gaps are not problems to be solved, or distances to be crossed by a sufficiently advanced technology. They are features of the universe's chosen structure. Gravity gathered matter into filaments and clusters and left the rest empty, and the rest turned out to be almost everything. That choice, encoded in the density fluctuations of the first moments after the Big Bang, is why the night sky beyond our galaxy is dark, why the distances we have talked about tonight exist at all, and why every star you can see from Earth is within the Milky Way. A single galaxy out of 2 trillion, one bright island in an ocean of intergalactic silence. We are grateful you are here with us tonight. We are grateful you stayed for all of it, the scales that do not fit any human comparison, the emptiness that makes our own galaxy feel astonishing simply for existing. The universe had no obligation to arrange itself into anything interesting. It did anyway, and we are among the interesting things it arranged. Remember that the distance to Andromeda is both enormous and negligible on the scale of what lies beyond it. Remember that the voids are not gaps in the universe, but its dominant texture. Remember that the observable universe is our personal horizon, not the edge of everything, and that whatever lies beyond it almost certainly doesn't know we are here. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together. Good night.